Hey everyone, welcome to the lecture for 9.2 on series and convergence. So this builds upon 9.1. We talked about sequences. Well, series are just a sum of given sequences. So notice that we have the same notation, curly brackets or curly braces, a sub n. That's going to be our sequence. And so in a series, you just take the elements of the sequence and you add them up. It's infinite because you add them up until infinity, right? So this is kind of like a hard thing that we're going to have to determine how to take limits of, and it's going to take a few algebraic tricks and clever manipulations to get that done. So just to reiterate, a sequence is a list of terms. A series is a sum of terms. So it's a list and a summation. This is our sequence. This is our series. So the way that we're going to determine what the limit of a series is, if it exists, is that we're going to have to look at partial sums. So partial sums just says, take the summation and then give yourself a stopping point, some arbitrary n, and then try to kind of consolidate that if you can. Then observe the behavior as n goes to infinity. And we'll do an example of how that looks. So for the first example, if the partial sum converges, then the series converges. And if the partial sum doesn't converge, then the series doesn't converge. So for the first example, we're going to look at this geometric series here. So the first thing that we want to do is we want to look at the partial sums. So our partial sum, so for the first one, s sub 1. So 1 as the subscript of s in our partial sum denotes the stopping point. So we go from n to 1, we look at our subscript on s, and we're like, okay, we're just going to the first term of 1 over 2 to the n. This is just one term. It's 1 over 2 to the first, which is just 1/2. And s sub 2 is the same thing, except we go up until 2. So 1 over 2 to the n. So this is 1 over 2 to the first plus 1 over 2 squared, and this is going to be equal to 3/4. S sub 3 is equal to n equals 1 all the way up to 3 of 1 over 2 to the n. So this is 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed. So this equals 7 over 8. I was entertaining the thought of showing you the derivation for the formula of finite geometric series. Suffice it to say that you could also notice a pattern here. The top number is always 1 less than the bottom number. So 8 is the largest power of 2. So really you get that s sub n, which is your generalized partial sum, which is 1 over 2 to the first plus 1 over 2 squared plus ... plus 1 over 2 to the n. It's going to be 2 to the n on the bottom, in as much as s sub 3 had 2 cubed on the bottom, s sub 2 had 2 squared on the bottom, and then we just subtract 1 to get our numerator here. So then if we wanted to determine the series, the infinite sum, n equals 1 of 1 over 2 to the n, it's going to be equal to the limit as n goes to infinity of the partial sums. So this is the big idea for this section, is that you want to express your series as a partial sum, take the limit of the partial sum, and that's actually the infinite sum that represents the series. So this is the limit as n goes to infinity. And we've already kind of consolidated and simplified what s of n is. So this is going to be 2 to the n minus 1 on top, 2 to the n on the bottom, and this is a very straightforward limit to evaluate. This is 1. So the limit for example 1 is the number 1. So that's how you do the assessment of a limit of a series. So in this case, because we got a real number that was finite, we know that the series converges. So next we're going to look at another example. So this is example B. This one's a bit interesting as well because what's going to happen here, we can take the partial sum. So S of 1 is n equals 1 to 1 of our series, or of our sequence inside the series. So 1 over n minus 1 over n plus 1 is called the summand, and then the whole thing is the summation. So we're just going to take the first term, which is 1 over 1 minus 1 over 2. And this equals, I'm actually going to leave it like this. I'm going to write it as 1 minus 1/2, and you'll see why in a minute. There's only one term, right? Just this first term here. Okay, so for S of 2, we start from 1, but this time we're going to go up to 2. So the first term is 1 over 1 minus 1/2. And the second term is 1/2 minus 1/3. So what's interesting here is that we'll get a cancellation. And we're left with 1 minus 1/3. And then for S sub 3, n equals 1 to 3. 1 over n minus 1 over n plus 1. And so that's going to be 3 terms for us. So we'll get 1 over 1 minus 1/2, 1/2 minus 1/3, 1/3 minus 1/4. And you'll kind of see the pattern that's happening in greater detail. So the 1/2s cancel, the 1/3s cancel. And what we're left with is 1 minus 1/4. So hopefully you can see a little bit of a pattern going on here. So if we were to go to S of n equaling 1, stopping at some arbitrary n of 1 over n minus 1 over n plus 1, and let's look at the last 2 terms. So we're going to get all this cancellation out. So 1/2 and 1/2. We know that 1/3 cancels out with something beyond the dots. And then we're also going to have 1 over n minus 1 canceling out with something within the dots. And then we're also going to have there we are. I was like, I'm missing something. This is a minus sign. Okay, super. So then we're also going to have the cancellation of 1 over n and 1 over n. So what we're really left with, the only thing that survives is the one, the very first 1 over 1, and the last guy 1 over n plus 1. So this is actually what we call a telescoping series. So now that we have S of n, we can compute the summation this is the limit as n goes to infinity of our partial sums. And we've computed our partial sum to be of the form 1 minus 1 over n plus 1. And this is another really straightforward limit. The fraction goes to 0 clearly, and so we're left with the limit of 1. So the series converges here. So let's look at a third example where we're not going to be so lucky this time. We're just going to look at the example where we just sum up a bunch of ones. So this is example C. So let's do the partial sums. So S of n, S of 1, S sub 1 is the sum from n equals 1 to 1 of 1. So we just write 1 one time. S sub 2, n equals 1 to 2 of 1. So I write 1, and then I add 1 to it, and I get 2. S sub 3, 1 plus 1 plus 1 is 3. So this isn't terribly imaginative, but what you can see is happening is that S sub n, which is the partial sum from n equaling 1 to n of 1 equals 1 plus 1 plus 1 plus da-da-da-da plus 1. We do that n times, and we just get n. So the summation from n equaling 1 to infinity of 1 equals the limit, as we've defined it, of the partial sum S sub n. And we know the general form for our partial sum is just n. So the limit as n goes to infinity of n equals infinity. So we conclude the series diverges.